And we want to use the box you guys are going to be using tomorrow for the first time. Stanford Signal Analyzer. Huge thing. Yeah, it's huge. That means it probably draws a lot of current. That would be the best thing to use. Okay? Oh, we got to get started. You know, there's always alternatives, right? But that would be, I think, the best. But you haven't used that before, right? The Stanford. Okay, well, tomorrow.
Yeah.
All you guys are going to. Okay, good. Okay, so I know this is kind of overwhelming when you first see it, but if you see it enough times, like anything, it's not that bad. But it is important for what we're going to be doing the rest of the quarter. And we showed these are all equivalent, and they're equivalent to the canonical equations of transduction. Those nice, simple equations. And we proved yesterday that this is equivalent. That was pretty easy. Okay. And now, let me, I think I mentioned this yesterday, but let me say it again. There is a bit of a problem here when we write down Kirchhoff's laws for this circuit. You know, Kirchhoff's laws hold for an electrical circuit. And, you know, technically this is not an electrical circuit because this is not a voltage, it's a force. It doesn't have the right units. So if you look at our derivation, we actually had, you know, I think we had, at some part we're going to have, because we think of the current through here as the sum of the two. We had that. And, you know, you can't add two quantities together that don't have the same dimensions. But it worked there because this canceled out. So it was okay. But that's an indication of a problem here. And this problem really has to be overcome because when you're going to use this, for example, to design, ultimately we want definite numbers for all of these quantities. Usually if you're designing a transducer or you have a transducer that you want to understand, we're going to have to put in numbers in here. So ultimately we're going to have to deal with voltages and currents here. There has to be some correspondence between the two, between the electrical quantities, the voltage and the current, and the force and the velocity. Now, it's best now, along those lines, okay? It's best now to skip these momentarily and go to E here. You'll notice E has it's different than A. It's clearly different than A. The structure's different. But what I want you to notice here is the fact that the force here has been scaled by this quantity. And the velocity here has been scaled by that quantity. These quantities this turns out to be a voltage, as we will see. And this turns out to be a current. So this is a proper representation of an equivalent circuit for the canonical transduction equations, where everything is it's a fully electrical circuit now. We don't have these mechanical quantities here. Okay, so how do you get to here? Well, we'll see that, but I think what we should do next is show that this is equivalent to the canonical transduction equations. So we'll postpone dealing with the transformer. We'll see that the transformer transforms this into this. That's what we're going to find. That's the purpose of the transformer. But for right now, let's just show that this is equivalent. So we look at let's look at the left loop, the simplest loop here. We have this step up in voltage here. That will be be balanced by the voltage drop across here. Okay, I like to do it as a balance rather than add all the voltages together. That seems more physical to me, and especially when we get into these complicated situations here. So I set V equal to the drop. The drop across here is the current times the impedance. The current is the sum of these two currents, right? So we should get this equation right here, and we can simplify it. And I want you to look at this equation now. See, V equals that. That's the first canonical equation. So we got the first one already. All right. Now let's go back and let's do the same thing. Let's look at the right loop now. Here we only have two loops here. So we do the same thing. This voltage here, this quantity here, must equal the sum of the drops along here. So I just add these two impedances, multiply by the current. That's the voltage drop here. And then I had the same voltage drop here that we had before. I set the sum of these drops equal to that. And here's what we get. This, the sum of the drops. And now you can see this is not very simple, but if you can do this in your head, if you go through and simplify this, multiply through, you get this, there's some cancellation. And then if you clear this factor here, multiply by T over ZE, you get the second canonical equation. So this is equivalent. This is an equivalent electrical circuit. Okay. So next, now we can't put it off any longer. We got to deal with transformers. So let me remind you, property of a transformer here. We use the standard mesh currents again for positive directions. We'll assume counterclockwise current here, counterclockwise current here. N is the turns ratio, so it's the ratio of the number of turns here to the number of turns here. And you remember the basic idea of a transformer is when you have an AC, an oscillating circuit here, this is generating a magnetic field, which in good transformers is highly coupled here. Essentially all these magnetic field lines travel through this inductor. So because it's AC, Faraday induction will induce a voltage across here. And it's well known that if you've got twice as many turns here as you have here, you're going to step up the voltage by a factor of 2, right? Okay, so we write this like this. The voltage across the secondary here is N times the voltage across here, okay? Now we also know that energy has to be conserved here. This is a circuit element, represents an ideal transformer. There's no resistance here. If there were, we'll put it in. We would add it in. So for an ideal transformer, the power coming in has to be the power going out. Okay, so the power is the current times the voltage. So we have to have, whereas the voltage is stepped up by N, the current has to be reduced by N so that we can conserve energy. Okay, power is constant. Okay, so that's what we're going to use these two relationships here. So let's look first of all at B. Okay, now you'll notice we have an additional loop here. So however, what simplifies this is that the voltage across here is, of course, because there's no impedances along here, it's going to be the same as the voltage across here. So we don't have to introduce a V prime, but we do need to introduce an I prime. So we'll call that using the standard mesh idea, right? You want to see this as I drew in this other diagram here. What you want to see here is a counterclockwise current going around that loop that has value I prime. We're going to call that I prime. Okay. So let's look at the simplest loop here. We got these three loops. Is this loop? Oh no, I better follow the notes here. Let's look. What's the voltage across here? Well, it's going to be, the voltage drop here has to be the same as this voltage here because of Kirchhoff's loop rule applied to this loop. So this has got to be V. What does this have to be?
N times V.
Right. It's N times V. Okay. And in here, and we'll talk about this more later, just accept it for now. N is this quantity. Okay. And the problem here is that it has dimensions. So our transformers here, which are abstract transformers, we call this often the ratio of the number of turns, but it's more general than that. It actually has dimensions, and you'll see why it has dimensions. It has dimensions for a very fundamental reason. But for right now, don't worry about it. Okay, so the voltage across here is going to be this quantity times the voltage across here. So we know the voltage across here. All right. So the next thing to do, I think, is look at the simple loop here. We write down. Okay, I better go to the, where is it? So if you look at that, we've got the voltage V. It has to be the sum of the drops. And across the electrical impedance, remember these mesh currents, we sum those two currents. And they're going both in the same direction. So we get that. All right. And now let's look at probably the right loop. If we look across the right loop, okay, it's very similar. We now have this F here, which we think of as a voltage. We do the same thing we did before. We're going to get this when we go through those two series. There are two series impedances. And then the voltage drop across the right side of the transformer, we just argued, has to be this. So that's why I have that there. Okay. Now, the next thing to do, logically, is to get rid of this I prime. So what's I prime? Well, remember, I prime, if you look at the transformer, we use this relationship right here, okay? But you need to realize that I prime is actually I1 here. So, and to apply this to our case, if you look at that, you're going to find that this is I prime. So I prime is N times U, which is going the other way, essentially going the other way than this. So I prime is equal to NU. That's good. We substitute that into the first equation. And then, editing this, when we do that, you can see this in your head, when we take this and substitute it into here and clean it up, we get the first canonical equation. So we're done with that. Okay, and now, what are we going to do here? Well, we don't have our independent variables of I and U. We just take this expression that we just got, the first canonical equation, substitute it into here. So we're headed towards the canonical form, right, where we have the only variables on the right side are U and I. And when you do that, you get this. So that proves that the first of the 5 circuits here, the first with a transformer is equivalent to the canonical equivalent. This one, that would be B right here. Okay. Now, don't worry, we're not going to do these right now. I think this is enough. Get overloaded on this. So this will be homework, I think. This will be homework, and there'll be a quiz problem, I think, related to this one. So I had to touch on we had to get to all 5, okay? So that's what we're going to do. That's the way we're going to handle it. Now, I do want to point something out here, and it's in the notes. This is actually easier than these two, I think. And the reason is, they all have these 3 loops, okay? But do you see what makes this easier than these two? I don't know if you can see it. What's the voltage across the left side of the transformer here? It's just V. What about here? So, and what about here? We don't know. So here, for these two, we have to introduce a V prime. Then we'll call V prime the voltage across this side of the transformer, and we have to eliminate it. So it's a little bit more complicated. And we'll do that tomorrow, right, for this one? Yes. Okay. All right, so now let's look at this issue here of the so-called turns ratio. Not only does it have dimensions here, but it can be complex. I mean, if we're going to be abstract, we might as well go all the way, right? These impedances, these can be complex. Remember, these quantities here in our canonical equations represent what's going on at some frequency, any frequency you want. They're functions of frequency. And you know that we can have phase differences here, right? So these are actually going to be in general. So it's actually, the turns ratio here is actually a complex dimensional number. And I didn't say it was complex here, but we'll put that in. Okay. So, if you look at this simple, the one that we're all familiar with, this diagram here, where is it? You look at this diagram here. Over here we have force and velocity. So, the transformer here, we usually think of the transformer here as just boosting the voltage. That's how people usually think of it. Here it's a broader, it has that scalar capability, but it's broader than that. It's actually turning, the way we want to think about it is, it's turning these units, this force, I want you to see this as a force and a velocity there. It's turning those into electrical quantities, into voltages and currents. And that's actually what if you think about it, that's what a transducer does. A transducer is a transformer, isn't it? And it's going to convert mechanical quantities into electrical quantities or vice versa. So it's very natural. The use of transformers here is very natural. It's just that it's not going to be a simple 2 coils wrapped on a form, some magnetic material, right? This is a lot more complicated than that. But the idea is the same. Okay, so the transformers are convenient, and you'll pick up on this as we go on in the course. Transducer people, I don't really see this, okay, but transducer people like to start off often with transformers. To them it has, I still don't get this, like I said, they have a physical feel for this, to transform between the mechanical and the electrical, or vice versa. But ultimately we want to eliminate them, and we will do this many times in this course. Ultimately, they're hard to deal with, of course, calculationally. So ultimately, we want to head towards this. This is the bottom line. So we need to be able to go from, let's say here, the one we just derived, or any of these. We need to be able to go from here to here. We'll call that eliminating the transformer. So that's what we're going to look at next. Here is eliminating the transformer. So we don't need to go through a detailed calculation, and the reason is we know that this is equivalent to this. Because this is equivalent to the canonical transduction equations. This is the same, and this is the same. Therefore, these two are equivalent. Mathematicians actually have a name for that, which is obvious, right? If these two are equivalent to something, they have to be equivalent to themselves. Yeah, mathematicians have a name for that. It's bizarre, right? Anybody know the name of that? It's called like nobody knows the name of that? Something to do with like transmission, transmittivity? I don't know.
Oh, yes.
Something, what? Sounds familiar?
Transitive?
Transitive? Could be.
I think that's what it is.
Maybe. Yeah, it sounds
Same
good.
thing as like
yeah.
A plus, if A equals B, then B
Yeah,
equals
right,
C.
there you go.
Yeah.
If A equals B and B is equal to C, then guess what?
Yeah.
Yeah, so evidently it's not always, because they have a name for it, it means there may be some mathematical constructs where it's not true. And that's what mathematicians do, right? They just dream up this stuff. And we ridicule them, and then 100 years later, it finds an application. This has happened again and again in history. I might have mentioned to you last quarter. So that's why you want to respect mathematicians. You just keep them happy, let them do what do whatever you want to do, you know. And they don't require much money or anything. They're just working all the time. You don't do experiment, you know, this is that paper or computer, that's all. All right, so anyway, it's clear that these two things have to be equal. So here's what we're going to do. We're going to simplify this, because we're going to be using this again and again in this course. Go ahead and absorb this into there, okay? In other words, it's not important, just get rid of this. Imagine it absorbed into there. Okay. I'm a little worried about something here. Yeah, absorb that into there. And then in general, here's what we have. Something's bothering me. In general, oh, I gotta go down here. Okay, so when we absorb that into here, we get this, okay? Now, yeah, okay, I'm gonna have to think about this. What we're about to say is correct, but I see that there's a potential. Hold on. So we simplify that first one. We similarly simplify the second one. And that's what's bothering now. We want to keep the equivalence, and I don't see that right now. I missed it when I was preparing. But here's what happens. The equivalence of those shows that this is equivalent to that. All right? And it's not, I have to admit, I thought it was obvious, but I'm wrong. I have to go back and think about it. But I'm sure that this is right, but it's clear I need to add some statements about that, so I'll do that. But anyway, you can show that. Now, here's what you want to remember. And I'll remind you this when we hit it. We're going to hit it, as I said, a number of times. What's happened here, the transformer, by removing the transformer, we've turned this force. This force gets turned into F divided by N, the ratio of the number of turns, which has dimensions. You can show that this has dimensions of voltage. All right? It's turned the velocity here into N times U, and you can show that when you multiply N times U, you get units of current, you get amps. And it's taken this impedance here. So this is easy to remember because the transformer works. So it turns this into a voltage, this into an actual current. You know, this is in volts, this is in amps. So that's fairly easy to remember. This is the one that is a little bit harder, but believe it or not, you'll get used to it. It turns out that when you take this mechanical impedance, lowercase m, right? Mechanical impedance, and divide by n squared, you get units of electrical impedance. So it's a fully electrical circuit here. All right, I'll check on this. Yeah.
Just backing to the last sentence, that paragraph there, we have absorbed T over ZE into Zm.
Yeah.
So it's Zm equals the old impedance plus or minus T squared over. So it's just a new mechanical impedance.
Okay, I think what you're asking is the thing what's bothering me about this. But basically what I've done here to come up with a diagram that we can use in the future I want to get rid of this. I've zeroed that out.
Okay.
Yeah, so it's not fundamental here. The diagram that we're referring to, it's this other one here. It's correct, okay? But yeah, I'm bothered by this too, and I should have foreseen this. We're basically killing this. Maybe absorbing it into here is not the right word. And that has the effect of, we're combining these and just calling it that. That has the effect we're killing this, which has the effect of killing that. That's the bottom line here. And I don't think I don't think that's obvious, is it? It doesn't look obvious to me.
I did.
It's not worth thinking about right now, believe me.
Okay.
But is that what you're trying, is that what you're getting at?
Yeah, why did it? Because we were looking at the circuit B and then it went to just mechanical impedance. I didn't know if there's any
right. So the circuit,
other than if it's just to make the diagram and
what we want is we don't need these complications here. We just need some impedance here and some impedance here for what we're going to do.
Makes sense.
So, but I agree with you. This is not obvious, and I screwed up. So I'll look into that. And it's probably there's probably a very simple way to look at it, but I don't want to take the time right now to do it. So anyway, I'll remind you in the future when we hit this. And you'll get used to it after a while. Removing a transformer, you'll get used to this 1 over n squared going in there, this being f divided by n, and this being n times u. So that's how transducer people think. They tend to think in terms of when they're coming up with equivalent circuits. They tend to actually start with a transformer in there, because that's like I said, that's what the transducer is doing. And then almost always you want to eventually eliminate it so that we can get down to an actual, real, purely electrical circuit. And then you solve for this, and then here's the basic idea of this course really. Once you solve for this, you can then go back and find the force. This could be, for example, if this is a transmitter, you could find the force that's causing the acoustic radiation. Once you've used Kirchhoff's laws to solve for this, you can find the currents that's involved. You can find the velocity, you can find the force. Doing all that can involve a lot of work, and it can be very complicated, and there are a lot of approximations that are made. Some of them you'll be disappointed, but as you'll see in this course, you're starting to see it. This is complicated stuff. So often we'll make pretty gross approximations in order to get to a final answer. So ultimately in practice when people do this, they rely on computer solution to electrical circuits. They get more accurate answers. But we want to do this, we want to keep this analytical, so we'll make these approximations. You'll see this a number of times in this course. And part of the whole procedure is going to be eliminating the transformer. So here is just a restatement of what I've said. And the units here, and I'm going to be editing this. The unit, you can show that the units of N is newtons. Now we have to be careful here, right? You've actually encountered this before, and you might have missed it. Most people don't, it doesn't bother them, they don't see it, and it doesn't bother them. But in here, sitting alone like this is this complex dimensional ratio of turns thing, right? This is newtons here. So don't get confused there. So N has units. You can show that it has units of newtons per volt. So it's converting, it's a conversion between mechanical Newton force and electrical force or voltage, which is volts. Alternatively, you can show that this has the same units of coulombs per meter, okay? And what a coulomb per meter is, if you take a coulomb divided by a second, so what's this? These are amps, right? A coulomb per second is an amp. And this, well, I'm just going to write U here. Okay, let me write the B. So what this is, these are the units of current divided by velocity. So you can see the conversion here. We need to convert between mechanical and electrical, and there are two quantities there. There's the voltage and the force, and the current and the velocity. Oh, and here's something. So you'll notice here, I think I did it right here. This, now that we've gone fully electrical, we use a capital M here. So it's because it's an electrical quantity, we use a capital letter. And this is a weird coincidence here. This M actually refers to two different things. We've taken the mechanical impedance and made it electrical, so it's gone from lowercase to uppercase. But the M also stands for motional. This is an electrical quantity that corresponds to mechanical motion. So we call this the motional impedance. And it's kind of nice, it's got the capital M there. It serves two purposes. To tell you that it's electrical, it's the electrical analog of the mechanical impedance, and it's also the motional impedance. And this we will carry this, we'll continue to do this. In here can be involved resistance, capacitance, and inductance, and we just use these capital letters. They all mean that we call those the motional resistance, the motional capacitance, and the motional inductance. And please remember here, these are electrical quantities. They correspond to the mechanical quantities. That's why we have the word motional in there. Okay. All right, so I'll check into this this problem, and I'll fix it. I'll put some writing in here. Anybody have any questions? Okay, so the next thing here is, you remember way back here, and it's very simple, nice simple transducer with that great demo. I'm still excited about that signal from the wire going up back and forth through the magnet. Wasn't that beautiful? You know, it's because the magnetic field was confined to an area here, and this thing was doing this big, large amplitude here. We got this signal, this voltage signal went like this. So when the wire is sort of outside the magnetic field, nothing's really going on. And then as it decays down, and the amplitude becomes smaller and smaller, and eventually it's within the magnetic field there. And as it gets smaller, the magnetic field gets more and more uniform because it's over, the displacement's smaller. It goes to a sinusoid. I thought, you guys didn't seem, we weren't crazy about that, but I guess I really like it because I know how noisy that system can be, right? And I didn't really fix it until just before class yesterday. Was that yesterday that we did this?
Yeah.
God, seems so long ago. Yeah, so we're going to be doing this in a video. This is going into a video, which will go into the website, the demo website. All right, well anyway, I stopped. We looked at this system, here it is, and we found, and it was not much effort. It was actually very different than the other electrostatic example. Because this is all linear, I think that's the main reason. We found that we do have the transduction equations, with the exception that they switch sign. Where am I? Well, I didn't write them out. So we have, it's not reciprocal, there's a sign change there, so we call that anti-reciprocal. So now that's what we want to look at that now and see how we can deal with this, how it is dealt with. So here are the canonical equations for an anti-reciprocal transducer. We go ahead and call this T. We don't need to use TEM or TME anymore. And we explicitly put in the fact that there's an opposite sign there. So because of that, we've shown, well, technically we didn't completely prove it, but because this is not reciprocal, and all electrical circuits are reciprocal, there's no equivalent electric circuit here. And that was just unacceptable to transducer people in like the first half of the 1900s. Okay, that was unacceptable. So that tells you something about how important equivalent circuits are for transduction. So somebody, or probably a number of people, fixed it. And this was, again, this year here, 1933. And it was noticed that the problem here is not, the problem is associated with the analogy that we're using, that we're so accustomed to that it seems so nice. Voltage and force correspond, and current, electrical current, and velocity correspond. And that analogy, as we've discussed, is not unique. You can flip. One way, you can flip these two right here. And let me go to this. It helps to see these diagrams. Let me go to the next one here. Okay, so when you flip these two and leave these alone, you get this. And now this is the mobility analogy. Voltage corresponds to velocity, and current corresponds to force. So what we want to do now is deal with the canonical equations, but instead of these variables being what we think of as the independent variables over here, okay, and these as the dependent. It's just, convenient to think that way. We're now going to switch. We're now going to go to here. So it's going to be I and F instead of I and U. So this is actually very easy to do. You can actually do it in your head if you want to. I'll just state it here. But to do this, we start with this, okay, with the anti-reciprocal case. And now we need to go to I and F. So I got to get rid of this U. So can you see how to do that? I solved the second equation for U. That's in terms of I and F. I put that in here, and then I'm going to have the right-hand side as a function of I and F. And this is what you get when you do that. When you do it, you get this. Okay? And, it's a little more complicated. It's to be expected, right? The canonical equations are written down assuming the impedance analogy. That's why they look simple. So this is what we get. Now, what about the second equation here? Again, we want I and F as our, so what do I do here? Wait, we want I and, I'm confused. We have this equation, okay, and we want to express U as a function of I and F. That's easy. You immediately get this, okay? So here are we've now transformed the canonical equations to the mobility analogy. Just change the variables, basically. And now I want you to look at this. The coupling, the transduction comes in here, and look at this. The transduction coefficient here, this quantity right here plays a role of the transduction coefficient. It's the same here. We now have a reciprocal system. We had to just change the correspondence, the analogy that we use. Instead of the impedance analogy, we go to the mobility analogy, and then we find that we have a reciprocal transducer, but we have to do it in the mobility analogy. Now, because this is reciprocal, an equivalent circuit will exist. And three of them are shown here. All right? Now, you would expect some complication, and it's handled. What's done to alleviate it is two things that we're going to see again and again in this course. We're going to use the admittance instead of or in addition to the impedance. The admittance is simply 1 over the impedance. We encountered that in a homework problem, I think, last week. And then, I think it's the first time we've seen this here, and this is an extremely important number in transduction. It's tabulated for different materials, for sonar materials. We'll see this again and again, especially when we get into sonar. It's a dimensionless number. You can easily show this is a dimensionless number, and it's a dimensionless measure of the strength of the transduction. You can see it's proportional to the transduction coefficient here. Okay? The bigger this is, the more transduction you get. And it's being normalized by the other impedances. So this is a kind of relative number. It tells you relatively how much transduction you're getting. And usually you want that to be big, you know. So when we use that, we can, here are 3. You can show that these are equivalent. Okay, we'll discuss these right now. So these turn out to be equivalent. And you can see, here's the use of the coupling parameter, or the coupling constant. And nobody seems to know whether the coupling constant is k or k squared. Okay? So you want to be aware of that. You see the way it's defined here. Most people deal with the square of this, and they'll actually call that the coupling parameter. So you just have to be careful about that. They use the same word meaning 2 things, k and k squared, which is unfortunate, but it's usually doesn't cause any trouble. Assuming you're writing it down. Okay, well, let's look at the first one here. If you go back and look of the 5 that we started off looking at here, you'll see that this is similar to the first one. Okay? It's not the same. It's roughly similar. You can see it's roughly kind of the same structure. And just as we showed there, you can easily show by using Kirchhoff's rules, you know, summing these, thinking this is a current, summing it here to find the impedance drop here, and using the loop rule, Kirchhoff's loop rule for each side there, you can easily show that this is equivalent, just like we did before. You can show it's equivalent to the canonical equations in the mobility analogy. The second one is similar to the one we started off, is the second of the 5. B, the one that we started off with the lecture doing, with the first transformer we dealt with. If you look, you'll see that this is similar. And if you apply the transformer rules that I diagrammed there for you, for us, you'll see that it's equivalent to the canonical equations in the mobility analogy. And then finally, we get the fully I didn't confirm this. We get the fully electrical circuit. Okay, and I'm hesitating because we don't really, this is a little different than what we dealt with before. Okay, so let me make a note here. But you can show, without a doubt, that this quantity here, F over the transduction coefficient, has the units of amps. Okay, and you can show that the transduction coefficient times the velocity has units, excuse me, yeah, has units of volts. So if you look at this, this is a fully electrical circuit. What we think of here, this is a voltage. So when we deal with this, we think of this as a voltage, and we think of that as, that's what this means, it's a current. So again, it's confusing because we're in the mobility analogy here. Yes?
So for part B, when you're using the transformer, you have to transform the force as if it's a current and the velocity as if it's a voltage across the transformer.
You know, when you, well, I'm not sure what you're asking, but when you want to write down, when you want to prove that these, you get the transduction equations in the mobility analogy here. You just use the you don't worry about, you think of this as a current.
Yeah, that's
you think of that as a voltage.
Okay.
Right, yeah. That's right. Right, there was, so,
Yeah.
pardon me?
You treat it the same way, you're just matching it to a different set of equations.
Yeah. Yeah, the mobility analogy is just, you know, it's just, the problem here is it's not very physical. And it's hard to swallow. But the idea is the same. It's getting kind of warm in here. Now, the other thing I need to tell you is we're not going to use this very much, okay? In one or two cases, I think, we'll use this. We won't use it very much. But it's there if you ever need it. Okay. So this is fully electrical at this point. I want to make some notes here. I want to go back, look at this, and clarify this. Okay, so what we're going to do in the next few minutes is pretty simple. This admittance that we were just talking about here, I didn't actually point it out to you, but yeah, you can see it right there. See the appearance of the admittance here. As I've told you before, it plays an important role in transducers. You want to get used to it. Things can be simpler in terms of admittance rather than impedance. So here's the relationship between the two. Impedance has a real part that's called the resistance. The imaginary part is the reactance, as you know. The admittance, which is simply defined to be 1 over the impedance, has a real part that's called the conductance, and the imaginary part is called the susceptance. And just because these are inversely related does not mean that these are inversely related. We talked about that before in the problem set, and I put it down here for you. Here's the admittance, 1 over Z. If we clear out make the denominator real, that's what I've done from going from here to here. I've multiplied by the complex conjugate of this, numerator and denominator, by the complex conjugate. We can see that the real part, the conductance, is this, and it's not 1 over R, right? And the susceptance is not 1 over X. It's given by that. And admittance offers a real good, it's a diagnostic tool when we electrically probe transducers, as you'll see in the lab again and again. Yeah, and we have boxes here that plot this for you. So we'll be able, as a function of frequency, these quantities. So you change the frequency, you're moving around in the complex admittance plane or the complex impedance plane. But often we're going to find that the admittance is easier to deal with. You get more information quickly, like you can get these nice circles. A circle tells you you've got a resonance. Okay? Now what we're going to do is we're going to talk much more about piezoelectric material. That's the standard material for sonar transduction. But at this point, just to make some progress here, what we're going to do is model this. I'm going to give you the standard model, and it'll make complete sense to you as I explain it. Okay? So let's begin here from an equivalent circuit point of view. The first one here, this is general. If you go back and look in the impedance analogy, all we've done is added a load here. The only difference is a load's been added there. So that's general. What's happening next here? This will be one of them that we dealt with. I can't remember. This is the third one. It's C of the 5. It's the third one of the 5. Okay? It's the same except we've added a load. Okay? Now, going from here, we've now specialized to the standard simple model of a piezoelectric material. And what it is just this. Here's the way you want to think about it. And the geometry can be different, but the idea is the same. You've got the slab here, and it's plated so that it's acting like a capacitor, but it can move. That's the mechanical stuff. The electrical stuff is that it's a capacitor, and the mechanical is that it can move. It's as simple as that. Okay. Now, how you actually get that with a piezoelectric material, we're going to spend a lot of time talking about that. Okay, the physics of it. But the idea is really simple. It's a capacitor that the distance can change. Okay, and that's how we get coupling. When you squeeze it, you get a voltage like I showed you in the demonstration, for example. So that's what we've done going from here to here. You'll see on the mechanical side, standard oscillator that you saw in 3119, right? Now, the left side is a little bit more complicated. Brian has left this here, and he doesn't explain this, okay? But I'll tell you what I infer about this. We've left this. We've now specified what this is. This is a capacitor. Okay, so this C naught here is the capacitance. When there's nothing coming from the mechanical side, it's called the blocked capacitance. What does blocked mean? No mechanical motion, U is equal to 0. So everyone calls this the blocked capacitance. And to make it a little bit more realistic, and this is, what's this? It's a leaky capacitor, right? The capacitor will, if you charge this up, this will cause it to discharge. Almost always, this is a very large number, and often we just forget about it, but he's put it in here just to be general. So that's called the leakage resistance. Okay? The capacitor doesn't stay, for whatever reason, it doesn't stay charged. You put a charge on there, it doesn't stay charged. And as we've seen, you know, in some cases you will have to supply that charge. Not for sonar material, typically, as we will see. It's permanently built in there because it's polarized. We'll talk a lot more about that. So that's kind of a nice feature, sonar material. Okay, now, look what he does. This is sleight of hand, okay? Goes from here to, it removes the transformer, right? You can go back and look at our prescription for what you do. You'll see there's going to be 1 over N squareds here. We got N downstairs here. The current has N upstairs. Everything seems fine, but he's done something else that he doesn't explain. What is it? Do you see it? He set this equal to 0. Okay? So the only thing I can think of here is that when you look at the impedance drop here is small. For typical sonar, you know, for typical piezoelectric material applied to sonar, this is going to be small compared to that. But unfortunately, he doesn't justify that. Okay, but I think we can infer that it evidently is small because that's exactly what's happening. All this stuff comes from here. This is just being reproduced there. That's gone. This has been shorted out. So I make a statement on that in here. Okay. All right. So we're going to pick this up on Monday. Oh no, Monday's a holiday.
Tuesday.
Yeah. Not that I care, but what holiday is it?
Martin Luther King.
Oh, okay. Sorry. Yeah. Holidays. Okay. To me, they're not holidays. They're research days. Okay. So we'll pick this up. We'll analyze the third circuit, and you'll start to see how useful this is in the laboratory. Ultimately, in the laboratory. The laboratory this week is quite simple, but it's important you get accustomed to the Stanford impedance analyzer. And you'll also be dealing with, there's actually 2 experiments you'll be dealing with there. So that's 3 o'clock, right? In the usual room, 107? Okay. All right.